Good afternoon, everyone. So, the last class in lecture 3, we have discussed about some of the important topics. So, in lecture 4, I'm Soumen from IT Kanpur Chemistry Department. So, today we'll start a lecture 4 from the chapter of organic chemistry, some basic principles and techniques. So, we'll start from the. So, in previous lecture, we have discussed a little bit about what is inductive effect and how the inductive effect helps in the stabilizing the carbocation or radicals which is formed in situ in the reaction mixture. In the reaction mixture, what kind of like the carbocation or the radical generated, and after that, how this inductive effect helping to stabilize the carbocation or the radical. So whatever we have known, the 3-degree carbocation, like in the previous chapter, I will just go through quickly whatever we have seen. So in the previous lecture, we have seen this kind of CH3. Suppose this is a methyl group. This is a methyl group. And this is another methyl. So methyl positive is the more stable carbocation compared to the any other carbocations, like a second degree, secondary, or primary. And this is the radical, 3-degree radical. CH3 or methyl is the same in the case of stability. If we are talking about the stability, then all are same. And this is also CH3. This is the CH3 radical. So these two are radical, and which depends on the stability of this radical also depends on the inductive effect. Okay. So now what we will discuss. So what is inductive effect? When a covalent bond is formed between atoms of different electronegativity, the electron density is more towards the more electronegative atom of the bond. Such a shift of electron density results in a polar covalent bond. Okay, such a shift of electron density results in a polar covalent bond. And if you see the CH3, CH2Cl, that is CH2 is the more positive charge, and CH3 is the less positive charge. Okay, in other words, the polar carbon-chlorine bond induces polarity in the adjacent bond. Such a polarization of the sigma bond caused by the adjacent polarization of adjacent sigma bond is referred to as the inductive effect. Okay, so what is inductive effect? So if you see this example, I have taken one example. Okay, CH3, CH2, Cl. Now here 2 CH3 is there and 1 chlorine atom is there, and in carbon atom 2 hydrogen attached, and this carbon atom 3 hydrogen attached. And if you see the structure carefully, chlorine is attached to which carbon is much closer to chlorine atom, and chlorine is more electronegative compared to these two carbon, right? So that means inductive effect is what? So when a covalent bond is formed between atoms of different electronegativity, so that means this is a covalent bond. This one is a covalent bond. Now they're saying when a covalent bond is formed between atoms of different electronegativity, the electron density is more towards the more electronegative atom. Now here in the 4 atom, so chlorine is the more electronegative. So obviously, so then electron density will go in this direction. So chlorine is more electronegative. That means electron density is going towards the chlorine atom. Now such a shift of electron density results in a polar covalent bond. So this is called polar covalent bond. Now the Cl will be delta minus, this will be delta plus, and this will be delta 2 plus. Okay, so now which carbon will be more electropositive? So that means this is the electronegative atom. So delta minus is generating on the chlorine atom, and delta plus is generating on the carbon atom. So that means, so more positive charge on the carbon atom, more negative charge on the chlorine atom, and this is the less positive charge. This is the less positive charge. Okay. Now, in other words, the polar carbon chlorine bond induces polarity in the adjacent bond. Okay. In other words, the polar carbon chlorine bond induces polarity in the adjacent bond. Such polarization of a sigma bond caused by the adjacent polarization of the adjacent sigma bond is referred to as the inductive effect. So, in other words, the polar carbon chlorine bond induces polarity in the adjacent bond. Such polarization of a sigma bond caused by the adjacent polarization and of adjacent sigma bond is referred to as the inductive effect. So this is called inductive effect. Okay, so we can also discuss another example. Instead of chlorine, if we take CH3, then CH2, and then NO2. Okay, now NO2 is also electronegative atom. So now here the electron density is going towards here. So this is also electron density. So NO2 is more electronegative. Electron withdrawing group is there, NO2. So this is also known as the electron inductive effect. So for this we can also explain what is inductive effect, right? So this is another example. So one example I am taking from the textbook and another example I am taking from the outside. So this is the another example where also people can ask this, what is the inductive effect in this case. So maybe people will ask in which carbon atom you have a more positive charge and which carbon atom is the less positive charge. So obviously this will be more, because why? So a CH2 is more close enough to the nitrogen atom. So this is why this is a more more and this is a less. So less positive charge. So this is a now this is less positive charge. Now we'll go to the next slide. So the effect this effect is passed on the subsequent bonds, and also the effect decreases rapidly. So this kind of inductive effect vanishes vanishingly small after 3 bonds. So okay, now we'll discuss this part, what they are trying to say here. So this effect is passed on to the subsequent bonds also, but the effect decreases rapidly as the number of intervening bond increases. Like how? So let's say for an example, we'll take this same example only, but instead of 2 carbon, we'll take now 4 carbon. CH3, CH2, now another CH2, now another CH2, now so after 3 1 2 3, so now another CH2, now it is Cl, let's say it is Cl. So now what will happen? So they are saying inter becomes vanishingly small after 3 bonds. So let's say this is a 1 bond, this is a 2, this is a 3, and this is a 4 bond, this is a 5 bond. Okay, so that means, so up to this one, so this is electron density. So electron density is going towards chlorine, right? Because chlorine is more electronegative. Now electron density is going towards here. Okay, now 1 2 3, so that means 1 2 and 3, so becomes vanishingly small after 3 bonds. So after that means up to this one there will be some inductive effect, but after this carbon and this carbon there will be vanishingly small, that means very small. We cannot count even in this carbon any inductive effect is there or not. That means this carbon atom doesn't have any kind of although it connect through after 4 carbon atom, although it is connect to a chlorine atom, but still it doesn't have any kind of inductive effect. So the inductive effect is related to the ability of the substituent to either withdraw or donate electron density to the attached carbon atom. So based on the ability, what they are saying. So based on the ability, so the substituents can be classified as electron withdrawing or electron donating. Now, electron donating groups relative to hydrogen, halogens, and many other groups such as halogen, and many other groups such as nitro, cyano, carboxy, and ester, alkoxy are withdrawing group. So what are the groups are electron withdrawing group? Like nitro group, cyano group, alkoxy group, carboxy group, ester group, okay, and alkoxy group are electron withdrawing group. Okay, now we'll discuss about the electron. So these are all the some kind of group which is known as the electron withdrawing group. Now we'll go to the next slide. So where the based on the ability also it is I shown there. So groups related to the nitro group, cyano group, carboxy group, ester group, alkoxy group. Alkoxy means suppose O and there will be one benzene. So this is OC6H5. On the other hand, the alkyl groups like methyl, ethyl, and are usually electron donating groups. Okay, on the other hand, the alkyl groups like methyl, ethyl are usually electron donating groups. Okay, now, so this is called methyl group, this is called ethyl group, and are usually electron EDZ, that means electron donating group. This is called electron donating group. Now the resonance structure. Now what is resonance structure? So there are many organic molecules whose behavior cannot be explained by a single Lewis structure. As per the above representation, benzene should exhibit two different bond lengths due to carbon-carbon single bond and carbon-carbon double bond. However, experimentally, benzene has a uniform carbon-carbon bond distance of uniform carbon-carbon bond distances of 139 picometer. A value intermediate between carbon-carbon single 154 picometer and carbon-carbon double bonds, that is 134 picometer. But so what happened? They are saying due to the carbon-carbon single and carbon-carbon double bond. However, experimentally benzene has a uniform carbon-carbon sigma bond distances of 139 picometer, a value intermediate between 154 picometer and the 134 double bond. Thus, the structure of benzene cannot be represented adequately by the above structure. Further, benzene can be represented by equally structure 1 and structure 2. So, what is resonance structure? So, you can see this is a benzene ring. This whole molecule is a benzene ring. Now you can see here and here one double bond is there, but this carbon to this carbon, one single bond is there. So this is a single bond. So 3 single bond is present here. Now the problem is here. So they are saying that the single bond, 3 single bond or 3 double bond is there, but experimentally, benzene has a uniform carbon-carbon bond distances of the 139 picometer, which has a value intermediate between the carbon-carbon single, that is 154 picometer, and carbon-carbon double bond, that is 134 picometer. Thus, the structure of benzene cannot be represented adequately by the above structure. This is the above structure. Now, benzene can be represented by equally structure 1 and structure 2. So, what is structure 1 and structure 2? If you see carefully, this is the 1 and the carbon atom 1, carbon atom 2, carbon atom 3, 4, 5, 6 in such a way. So if you can just organize in such a way. So here one arrow is there. So then it will go in this way. So then now you can imagine here this structure and this structure are just I will just another structure of the canonical structure of the structure one. So now benzene can be represented in such a way. That's why they are saying that. That's why in the previous slide they are saying. So benzene experimentally benzene has a uniform carbon-carbon single bond distances. Carbon-carbon bond distance of 139 picometer. So neither benzene has a accurate carbon-carbon carbon-carbon double bond. Neither it has a single bond. So it has a bond distance, a uniform carbon-carbon bond distances between the 139 picometer, a value intermediate between carbon-carbon single bond, which is a 154 picometer, and carbon-carbon double bond, which has that which the distance is the 134 picometer. So the intermediate between this bond distance 139 picometer. Now you can see this is the two structure, but rather it is a hybrid of the two structure called as a resonance structure. So this is called the resonance structure. So benzene can be represented in two structure. Benzene can be represented in two ways. So one is the structure one, and another one is the structure two. So in this way we can represent. So now going to the another example. So whatever we have discussed in the previous slide, that was a aromatic one. So this is called aromatic structure. This is called aromatic regenerating structure. Okay. Now we'll go to the one aliphatic. Aliphatic means non-aromatic system. This is called aliphatic or non-aromatic. Aliphatic or non-aromatic structure. So non-aromatic structure is what? Non-aromatic structure is like in this CH3NO2. So this is double bond. So CH3NO2, it can be written as a nitromethane. Me means CH3 and this is the NO2. NO2 can be written in this form. N double bond O, this is plus, this is minus. So therefore the actual structure is the resonant hybrid of the two canonical form of the structure 1 and structure 2. This is the structure 1 and this is the structure 2. So it can be written. So this is the actual structure is resonance. So therefore the nitromethane actual structure is resonance hybrid of the two canonical forms 1 and 2. So two canonical forms of 1 and 2. So now O minus is going here, and now this double bond is separating here. Now this double bond is going to the oxygen. Now this O minus is going to the NO bond. Now this plus. So in the other way around, so if it is a minus, then also we can also write in this way. So then what will be? The O minus will come here and it will be gone there. So it can represent in two structures. So structure 1 and structure 2. So now the energy of the actual structure of the molecule is the lower than that of any of the canonical structures. So the energy of actual structure of this molecule is lower than that of that of any of the canonical structures. So the difference in energy between the actual structure, the difference in energy between the actual structure and the lowest energy resonance structure is called the difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy or the simply resonance energy. So let's say what they are saying actually. So the difference between energy between the actual structure, let's say actual structure molecule is the here. Now the actual is the lower than that of the canonical structure. So now this is the actual structure molecule, and the lowest energy resonance structure is the, let's say, this one. Okay, because they are saying that the energy of actual structure of the molecule is lower than that of the canonical structure. So let's say this is a canonical structure, CS canonical structure. Now this is the actual structure. Okay, let's say actual structure AS and CS is the canonical structure. Now they're saying the difference in energy between actual structure and the lowest energy. This is, let's say, lowest energy resonance structure. Okay, resonance structure or canonical structure is structure is called the resonance stabilization energy. So this is the stabilization energy. That is why they are saying the energy of actual structure of the molecule is lower than the lower than that of the any canonical structure. So this is the stabilization energy one molecule has. Okay. Now we'll go to the next. This is the question answer section of this part. So what is the question? So what kind of question we can people can ask here? So one is the electronegativity is defined as the power of an atom in a molecule to repel electrons towards itself, attract electrons towards itself, or expand itself, or all of the mentioned. So first we'll understand what they are asking. What is the question? So electronegativity. We know that electronegativity is what? So which one has the more electron and more electronically more negative? So that atom will takes the electron from the electropositive atom. So electronegativity is defined as the power of an atom in a molecule to repel electron towards itself or attract electrons towards itself, expand itself, or all of the above. So we know that electronegativity, if any atom, let's say most electronegative atom in the periodic table is so let's say fluorine atom. Fluorine, then oxygen. Okay, and the halogen family is the chlorine, bromine, nitrogen. So these are all electronegative atoms. So let's say we'll take an example. HF. Now who is the more electronegative atom? Now let's say fluorine is the more electronegative atom. Now fluorine has a more electron density to it has a, so obviously hydrogen and fluorine, who is the most electronegative? Fluorine atom compared to hydrogen. Now it will pull the electron from hydrogen towards itself. This is called attract electrons towards itself. So that means electronegativity is defined as the power of an atom in a molecule to attract electrons towards itself and repel electrons towards itself. When it happens, this is called electron affinity. Okay, so electron affinity and electronegativity is vice versa, is the different opposite phenomena. So we'll not discuss here what is electron affinity, and what is the difference between electron affinity and electronegativity. But we'll discuss some of the things. We can also discuss for this question some of the other examples, like let's say CH3. Now carbon is there and chlorine is there. So in between carbon and chlorine, who is the more electronegative atom? Obviously chlorine, because chlorine belongs to the halogen family. Okay. So now if chlorine has the more electronegativity, then obviously electrodensity goes towards its chlorine. So now it will go like in this. So now the most of the electrodensity is going towards chlorine. So now it is a whole molecule is known as the CH3 scale. The electrodensity is going towards chlorine. Now you can see so it is also matching with their answer, attract electrons towards itself. So that means the bond is forming by sharing of the chlorine lone pair with the CH3 one lone pair electron. So now this whole bond electron density is going towards the more electronegative atom, which is the chlorine. So that means electronegativity is defined as an atom in a molecule to attract electrons towards itself. Now we'll take another example with oxygen. Okay. So now electron density is going towards oxygen atom. So now the electron density is going towards oxygen atom. That means carbon is getting more positive charge. So now carbon is getting more positive charge compared to oxygen. So that means, so here as carbon is less electronegative compared to oxygen, so then the electron density from the bond will go towards the oxygen atom, because oxygen has a more electronegativity compared to the carbon. Now we'll go to the next question, that is the factor on which the electronegativity depends upon. The factor on which electronegativity depends upon the valence state of atom, hybridization, both valence state and hybridization, and none of the mention. This is really a good question. I will explain it here properly. Okay. So what are the factors depends on the electronegativity? So what are the factors depends? Obviously, the valence state of atom. That means oxidation state, valence state of atom. That means and also the hybridization. Also, it depends on the oxidation state. So suppose let's say one atom, and one atom is the oxidation state is a, suppose we will compare. So we have to comparison means we have to take two different two the same atom with different oxidation state. So let's say one atom is the oxidation state is a +1 and another atom oxidation state is a +3. Now which has a +3, that means what? If any atom has +1, let's say for an example, we'll take the example first. Better to take an example. Let's say A is in +1 and A is the +3. Now let's say in which has the +3 oxidation state, it has a more electron deficient species, because compared to A plus 1, that is it has a less electron deficiency compared to the A plus 3. So obviously when someone has a more electron deficiency, so that means that atom tends and has a tendency to take a electron from somewhere, which can give easily. So that's why the A plus 3, which oxidation state has a more oxidation state, that atom has a more electronegativity compared to the which atom has a +1 oxidation state. Now, if we have a something like A plus hybridization, so hybridization also does matter. How? So let's say one hybridization is a carbon. Now this is a sp3, this is sp2, and this is a sp. So now if you see, when you are coming from here above to below, the which character is increasing? S character. S character is increasing and P character is decreasing. P character is, and this side, because we are going from SP, SP2, SP3. So P character is here, P character is increasing. So P character is increasing from bottom to top, and top to bottom is the S character is increasing. Now we'll discuss about what is the order of electronegativity from when you are going from sp to sp3. So if you see, so always remember one thing. So whenever you have a sp hybridized atom, so that means we have a sp means more s character, means more closer to the nucleus. So that means nucleus always have a greater tendency to attract the electron towards itself. So obviously, which orbital has a more closer to the nucleus, it has a more electronegativity compared to the anybody else. So that means if we see, if there is any comparison between sp, sp2, sp3, so s character is which orbital has the, which hybridization has the most s character. So that means sp has a more s character compared to the sp2 and sp3. Now we can say, so compared to sp2 and sp3, the sp3 has a more p character compared to more p character, and now more p character, sp3 has a more p character, and sp Yes. So sp3 has a more p character. That means it has a less electronegativity compared to the sp. So sp has a more electron negativity. Sp hybridized atom has a more electronegative compared to the sp3 atom. Okay, now it's clear the how the hybridization and the so valence state it depends on the electronegativity. So that means that if we see the option valence state of atom, obviously it also need valence state of the atom. If someone has a plus one plus three, obviously when the more oxidation state, that means which has a more electronegativity. And now the hybridization, if the hybridization has also sp3 sp3d2, so this kind of also depends on the both also. So that's why we need both sp as well as the sorry, hybridization as well as the valence state of the atom, or none of the mentioned. This is not possible. So obviously the option will be C. So we can also now you can tick this one. So we have a option C where which connected both valence state as well as the hybridization. Okay. Now we also explain the how this it depends both valence state and the hybridization. Right. Now we'll go to the question number three. So where question number three, where question number three is saying that, so how does this electronegativity get affected with the negative oxidation state? Now, yes, how does the electronegativity get affected with the negative oxidation state? It decreases, it increases, it remains constant, and none of the mentioned. So electronegativity, it depends on the which on the what are the parameter first. We have to see. So let's say if someone has a negative oxidation state means what? Negative oxidation state means already electronically saturated. And when it is more electronically saturated, so that means negative oxidation state. That means it has a negative charge. So if you see the before in the previous example where they are asking about the electronegativity parameter. What are the parameter depends on the both valence state as well as the hybridization. Now we'll come to a conclusion that obviously valence state also depends, but it doesn't depend always because of the negative oxidation state. So negative oxidation state is what? So it decreases, increases, it remains constant, none of the above mentioned. Now we'll go to the we can go to an example where it can be possible to, so we can discuss one example where we can see the what kind of negative oxidation state are available in organic chemistry. Then we'll go to the why it is none of the above. When it decreases, it increases. Why it is not decreasing? Why it is not increasing? It remains constant. Of the mentioned atom. But the question is important. Why the question is important? Because they are not asking about the, they are asking how does the electronegativity get affected with the negative oxidation state of what? Negative oxidation state of obviously atoms or metal or atom. So in a atom negative oxidation state is negative oxidation state is not possible, right? Why? Because one atom cannot be a negative oxidation state. The molecule, whole molecule can be a negative oxygen means negative charge ion. How? Suppose we'll take a metal complex. Now we need negative oxidation state of the metal. Now, so Cn is the, so 4 Cn is there, 4 minus electron, and 2 Co, that means neutral. means L type ligand. So first I will discuss about the what is L type and X type. So L type means neutral, and X type means anionic. L type is the neutral ligand, and X type is the neutral. X type is the anionic ligand. So now you can see so there are six atoms, six molecule, right? So metal can come. M equals to metal. Let's say M equals to metal. M equals to metal. Now let's say if M equals to metal, so then we have a four. So Cn minus, right? Cn minus is the anionic ligand. So that means this is the X type ligand. So how many Cn minus we have? So 4 Cn minus we attach to the metal M. So that means we have a 4 X type ligand. Now we have a 2 CO ligand. CO is the neutral ligand. Okay. Now what will happen? So neutral, that means we have a 2 L type ligand. Neutral ligand means L type ligand. So 2 L type ligand and 4 X type ligand. Now we have a 4 X type ligand, 2 L type ligand. Now what will be the oxidation state? The whole charge is 2 minus. Now what will be the oxidation state of the metal? Now plus 2. Because so then only the whole charge will be 4 minus. So whole charge is the 4 minus, right? So and the metal, the whole charge will be the minus 2. Whole charge is the minus 2. But 4 minus is coming from the X type ligand. Then plus 2 is coming from the metal. So obviously, so then metal is the plus 2 oxidation state. Okay, I'll erase this part because we don't have this one space. I'll first erase this part and I'll write here. So then, so where I yeah, I was discussing the metal is the plus 2 oxidation state. Like same way, if we take another example where metal is a plus 3 oxidation state. So then, so if they are asking them how does the electricity get affected with the negative oxidation state? Okay. So it doesn't, it decreases, it increases, it remains constant, none of the above mentioned. So it is not possible because of the maybe we don't have a proper example here, but I will definitely discuss one example. I'll check it whether we have this kind of any example which can directly means correlate with the negative oxidation state of the. So you can see negative oxidation state is the here is a negative oxidation state. Why it is a negative oxidation state? Because if you see the negative oxidation state, the whole molecule is the minus charge. So maybe, that is why maybe they are asking the negative oxidation state of the whole molecule, but actually the metal is the plus 2 oxidation state. Okay, so that's why it depends on the oxidation state of the metal or atom. It doesn't depend on the whole molecule oxidation state. So whole molecule oxidation state may be different. Like somewhere you can see plus 2 or plus 1 or minus 1, minus 2. So it doesn't depend on this one. So that's why they are saying it doesn't decrease it. It never, it will not increase it. It will not remains constant. So that's why the option will be the D. So best option will be the D. Even I can also take another example. Okay, maybe the next class I will discuss these things. I'll bring another example and I will discuss this question particularly. Although, because if you can see, so another example, if I draw another example, let's say metal. Okay, Cn, 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 CO, CO. Now let's say instead of this one, I will take the 3 CO molecule. 3 CO. So 2 minus. So now let's say the whole charge is the negative. So this is also minus. This is also 2 minus. But here oxidation state is the plus 1. So now it depends on the metal oxidation state. The electronegativity depends on the metal oxidation state, not in the whole charge of the negative charge. So because this is also minus 2, this is also minus 2. It doesn't depend on the, but it depends on the Central atom, in case of complexes, this is complex because metal is ligated to the some other ligands. So that's why it's known as a complex. But it depends on the oxidation state of the metal, not the whole charge of this molecule. Okay. Now we'll discuss about this example where the electronegativity of the hybridization atom will be, what are the the electronegativity of the sp2 hybrid atom will be, which one, 2.75 or 3.29 or 2.48 or 3.69. Maybe that we have to recall because we cannot like say this kind of thing. So that we have to remember that what are the means mainly what are the electronegativity of the atom you need to remember. That is the main thing I can tell you. That is the one is the fluorine atom. Okay. And another one is the nitrogen electronegativity, oxygen electronegativity, carbon, and hydrogen. If you remember these five, then your whole organic molecule will be, you don't need to remember even the whole periodic table atoms electronegativity. Only these five is sufficient for the NEET and joint exams for the electronegativity. You just remember these five atoms electronegativity, then it will be good to, it will be good actually, it will be good to remember these five. Then you can also solve many questions, like there will be at least one or two questions from the electronegativity part. So maybe if the time permit, maybe the next class I'll bring something about. So today not we don't have much time, so maybe I can discuss the what is the electron affinity. Okay, electron affinity and the electronegativity. Electronegativity is the means attract electron towards itself, who has the more electronegativity. But electron affinity is the different, means almost same, but electron lover. This is called electron lover, and someone called. So I will discuss it. This thing: electron affinity, electron affinity, and electron negativity. I will definitely discuss in the maybe next class. We have some interesting topic. The next class, maybe if the time permit, I can discuss around 10 minutes about the electron affinity, but not today class because today we don't have much time. So what we have discussed so far, so we have discussed about the today class, we have discussed about the inductive effect. So inductive effect, you know that inductive effect is the, so the main thing is the inductive effect is the depends on the how close your atom is to the more electronegative atom. So how close, if it is a more positive, if it is more closer to the the electron withdrawing group like chlorine, nitro, or chlorine, like electron withdrawing group like chlorine, nitro, carboxy, cyano, ester, these are all groups, or alkoxy group, then it will be more positive charge. If it is the far apart from the electron donating, electron withdrawing groups, then it will be less positive charge. Okay. And also remember one thing, so it becomes vanishingly small, very small after 3 bonds. After 3 bonds, it will be almost vanish. The inductive effect is related to the ability of the substitution of the electron withdraw or electron donate electron density to the attached carbon atom. Obviously, electron positive inductive effect or negative inductive effect. I have already discussed this thing, and this is the brief of this inductive effect. Then also we have discussed about the resonance structure. So resonance structure of the only I have bring two structure. One is the benzene, that is the famous structure. The resonance structure of this benzene can be represented in two ways. One is the structure 1 and the one is the structure 2. So I am just going through quickly in the whole slide. So structure 1 and structure 2, where you can say how the experimentally benzene has a uniform carbon-carbon bond distances between the 135 pico 139 picometer, and one is the structure 1, structure 2. You can see, and another example I have discussed, that is the nitromethane. That is therefore the actual structure is the resonance hybrid of the two canonical forms 1 and 2, and the energy of the actual structure of this molecule is the lower than that of the any of the canonical structures. The difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy, or simply and the resonance energy. Okay, therefore the actual structure is resonance hybrid of the two canonical forms 1 and 2. And this is the electronegativity is defined on the power of the electronegativity. As I informed you, as I already explained it, the attract electron towards itself. Okay, attract towards electron towards itself. And the second question was the how the electronegativity depends upon the both the valence state and the hybridization. This is also I have given two example. One is the sp case character, and another is the oxidation state hybridization as well as the oxidation state. And the third question was on the how the negative oxidation state does matter on the electronegativity. That also I have discussed two examples, but obviously I'll bring one single. This is the complex molecule. It is much more difficult to understand in this level. Maybe I will bring one particular example for this topic. I have to check it. I don't know whether it is in the textbook or not. I'll bring definitely in the next class. And the question 4 is the electronegativity of the sp2 hybridized atom will be what will be the electronegativity of the sp2 hybridized atom. So it will be the 2.75. And one more request from my side. So you can also remember. You have to remember this 5 atoms electronegativity. So fluorine, nitrogen, oxygen, carbon, and hydrogen. This 5 atom is sufficient for the to remember this electronegativity. Okay. So thank you for this topic. Maybe next class we'll bring something new, and we have to obviously we have to learn everything every day, every new things. So it will be better for us, me as well as you also. I am also learning in this step. Okay. Thank you.